In today's lecture, we're gonna continue talking about different types of chemical equilibria. Now, last week we talked about solubility product equilibria, and this week we're gonna quickly talk about the acid-base chemical equilibria. Now, the objectives for this chapter is especially for you to be able to be acquainted with the manipulation of monoprotic and polyprotic acid equilibria systems. I also like you to understand, one major application of acid-based chemical equilibria is their use in buffer systems. Very, very important in lots of different environmental and physiological applications. I also like you to underline or understand the key features, in pH titration curves, which are essentially fairly useful in volumetric quantitation of acids and bases. Now, you're going to find probably in the environment or in nature, if I can underline one type of chemical equilibria that is most important, I would say acid-base chemical equilibria is probably one of the most important chemical equilibria systems out there. And so I think it's very important, for you to understand, the mechanics, of these type of reactions, acid-base reactions. So you'd find acids and bases essentially everywhere. I'll take a few examples. Such as in the pharmaceutical industry, most of the drugs we take out there are either acids or bases. A good example is sildenafil. I assume none of us takes it. But it's an important compound that was serendipitously discovered by Pfizer, a pharmaceutical company, where they were trying to synthesize cardiac based drugs, and then they discovered this type of drug that was not very good in cardiac applications, but it turned out to be fairly useful in male sexual health. Of course, most of us know it as Viagra. Now you can see from the structure, and I like you guys to be able just purely to look at the structure and be able to indicate, whether it's an acid or whether it's a base. Like you can see this kind of structure and you can tell it's a base. Other examples, of very common organic acids out there would be the benzoic acid. If you take any natural organic matter, you're going to find that one constituent of it is benzoic acid, hydroxylated, and so forth. If you take lignins, which are very common in the structures of trees, you're going to find that the monomers that make up lignin are actually hydroxybenzoic acids. And of course, you can tell it's an acid because of that carboxylic acid group. Now, if I would classify acids and bases, they are often classified as either as strong acids, or strong bases, weak acids and weak bases. Now, strong acids mean that the acids, can be hydrolyzed or can dissociate, completely, 100% dissociation. So you're going to find most of the mineral acids, hydrochloric acid, perchloric acid, nitric acid, sulfuric acid, and so on. You're going to find those are strong acids, meaning they dissociate completely to give you a proton, or what you call a hydronium ion. On the other hand, strong bases, they are chemical species that hydrolyzes, completely, 100% hydrolysis. And good example, and of course hydrolysis means that one of the products that you're getting is a hydroxide, hydrolysis, meaning one of the products you're getting is a hydroxide. And that's what a strong base is, 100% dissociation or hydrolysis. Now, examples of strong bases, would be ionic hydroxides of either alkali metals or alkali earth metals, so elements in the group 1 and group 2 of the periodic table, the hydroxides, of those ions are basically strong bases. Other examples, of strong bases would be what you call the Grignard reagents. Some of you who are in organic chemistry know about that. So if at all you've got something like this, alkoxides, ions, and Grignard reagents, you're going to find that they are strong bases, meaning, they hydrolyze completely. Other examples of strong bases would be quaternary ammonium hydroxides, structures, that look like that. Now, on the other hand, weak acids and weak bases, they dissociate partially, so take note of that distinction. They dissociate partially, whereas, weak bases, they hydrolyze, partially, of course, to give you one of the products, which is hydroxide. Examples, of weak acids would be technically anything that has got a carboxylic acid, or anything, that is a protonated amine, you would find, that is a weak acid. So in essence, conjugate acids, of weak bases, are weak acids. Okay, I hope that's fairly clear. On the other hand, weak bases, often it's anything that contains, a deprotonated amine group, such as ammonia, and of course you get hydroxide on the other side, and of course we know that this one is a conjugate acid. So this is a base, this is a conjugate acid, and that's what we said. Weak acids, are conjugate acids, of bases, and vice versa. For example, this one here, which is an acetate, would be a weak base. So a conjugate base, of a weak acid, essentially it's a weak base. And then hopefully again, that is fairly clear. They dissociate or hydrolyze partially. Now, take note of this, there are some chemical species that behave both as an acid and as a base, meaning they can donate a proton and they can be a proton acceptor at the same time. A good example, of course, would be water. Water can hydrolyze, to give you an acid, but so also, can it give you a base. And we know that the dissociation constant of water is what you call Kw. I think sometimes we will call it the autoprotolysis, the autoprotolysis constant. All right? Essentially, that's one example of an amphiprotic species. Water is an example of an amphiprotic species, meaning that it can give you a hydronium ion and that it can give you a base, which is a hydroxide. Other examples, of amphiprotic species, would be, things like this. If at all you've got a polyprotic acid or a base, the middle species, often would behave as an amphiprotic species. I'll give you an example. If at all you had phosphoric acid, phosphoric acid, we know that this one has got up to 3 hydrolyzable protons. I can lose one, and when I lose one, I get HPO4, 2 there. And essentially, this is an amphiprotic species, because it can go back in this direction. And so also, can it go in this direction, to give you, this one, a monohydrogen phosphate. So hopefully you can see that is an amphiprotic species, meaning I can get it to hydrolyze to give me a base, but also, it can capture a proton, to give me a base and give you phosphoric acid. But also it can lose one of these protons, to give you a monohydrogen phosphate and hydronium ion. So again, that's an example of an amphiprotic species. So there are many amphiprotic species there, especially, for polyprotic acids or polyprotic bases. So I assume most of you are fairly familiar with the manipulation of acid or base chemical equilibria. I'll give you a quick example here. If I got a base, I'm going to symbolize it as a B. And then it will react with water. Of course, we know bases capture protons. So it would capture a proton, to give you that, which is a conjugate acid, of this base. And of course, I'm gonna get a hydroxide, which is really the definition of what bases are, or the active, ingredient, of a base. We all know that to do a chemical equilibria expression, we take the products and then we divide it by the reactants. And of course, you can see that the products, the concentration of them raised to their stoichiometry, in this case it's 1, 1. And divided, by the reactants, which is the base. We ignore the water, because it's only a solvent, in this case. Now, and then, of course, you can get the respective concentrations of the product. Often we would say it's X, because we don't know what it is. So that's X, that is X. And that would be the initial concentration or the formal concentration minus X. And so that would be sort of the equilibrium chemical expression, for this. Okay. Then maybe I quickly give you an example, although I know you did this, in Chem 102. Assume you got cocaine. Hopefully you don't use it, but you got an example of a weak base such as cocaine. Now, cocaine can undergo hydrolysis, and that is the base hydrolysis constant of cocaine, to give you the conjugate acid of cocaine. And of course, you can see what I did is I protonated, this guy. So I captured a proton, it got protonated. And so that's what essentially I'm calling, the BH plus up there, if I would symbolize it. And of course, I would get, the hydroxide, that remained after I captured, that hydrogen. So the question is, calculate the pH of 0.0372 molar concentration of cocaine. And again, fairly straightforward, I would set up, my reaction, the base, the cocaine reacts with water to get that. Initially, that is my concentration, which is there. The change, given enough time, the base hydrolyzes, to those constituent, products. So I'm going to lose X moles. And because I want to one stoichiometry, I'm going to gain X moles of the conjugate acid and X moles, of the hydroxide. And after given enough time at equilibrium, I'm gonna get, what I had initially minus what I lost. And then I'm gonna get the X, what I gained, after the reaction, and X for the hydroxide, what I gained. I substitute it into the equilibrium expression, and that's what I get. Now take note of this, I can make these assumptions, all right? That 0.0372 minus X is approximately equals to 0.0372. And essentially what we are doing is this. We are assuming, that the hydrolysis constant is fairly small. And so if you look at the amount of the products obtained, it would, the amount of the product the amount of the reactant, that was lost here, X, is not going to be as significant compared to what you initially started with. And the whole idea of doing this is to try to make sure we don't solve a quadratic equation. Of course, if we need to, we can. So we make that approximation. And then, of course, now I can calculate what my X is, based on my simplified formula. And then you're going to see my X, which is equals to hydroxide, is equals to 0.0031 molar concentration. The negative log of that, is 3.51. And of course, you can calculate the pH. We know the pH is equals to pKw minus the pOH, right? And you get the pH is equals to 10.4 or 10.5. take note of this. When you make this approximation, you always have to check if it was valid. And the way you do this, you check the 5% rule, or really what you call the percent dissociation, which is you take the number that I got, my x, I divided by what I had initially, I multiplied by 100, and I'm gonna check, my percent dissociation should not exceed 5% for you to have been able to make that approximation. As you can see, in this case, 0.8%, meaning it's very, very small, meaning it's actually a correct, way to do the approximation. So hopefully that's clear, a weak base, type of a problem. And again, you can see how important really it is. The reason, why you've got people who take drugs sometimes, they get intestinal irritation, is because of that. Most of the drugs are actually fairly strong bases. You can see, the pH, is around 10.5, for this solution if you take it. So of course it's gonna irritate the intrauterine, the intestinal walls and so forth. So key applications of acid-base equilibria, of course, they are used a lot in drugs, in pharmaceutical formulations and so forth. But also I think one of the key importance of acid-base equilibria is the fact that you can use them, in buffer formulations. And of course we know buffers, are mixtures of an acid and its conjugate base pair, all right? And meaning, that if at all you've got a buffer, it can prevent, things like acidosis, from happening and so forth. So that's one major application, of acid-base equilibria, being able to use it to make buffers. And there are many, many applications of buffers out there. I'll give you an example. If at all you're doing an enzyme catalyzed reactions, now, enzymes are only active at very specific, buffer regions. I'll give you an example. Trypsin, a very common type of an enzyme, physiological enzyme, a chymotrypsin. And it can only be used to digest proteins, specifically, at around pH of 8. And so for the protein to be digested properly, it needs to be in a buffered system. So you can see, very, very useful in physiological processes. When you take the proteins, they need to be digested, using enzyme hydrolytic reactions. And enzyme hydrolytic reactions happen at very specific pHs, meaning, you need to be buffered to be able to digest, the proteins. Maybe other types of examples of where buffers are critical, is if you're doing EDTA types of titrations, all right? If at all you're doing EDTA, it needs to be protonated. It needs to be protonated, for it to undergo, titration type of reactions. Maybe even go back to what you guys did with the spectrophotometric titration, that you did. You took iron 2+, I think it was 3+, and it was 2+, sorry. And then you reacted it, with bipyridine. And if you guys remember, you used a buffer in that system. You used sodium acetate for this reaction, to be able to happen. Because bipyridine is a base, and you want that base to be available in the deprotonated form, meaning it has a lone pair of electrons, so that, they can react with the iron 2+, to form the iron bipyridine complex. So you remember, you really had to buffer that system, the spectrophotometric determination of iron lab, for it to actually work. So again, buffers, very, very useful, in many different types of, reactions. And as I have said, they are fairly useful in physiological and biochemical reactions, especially, when you're dealing with enzymes. And all of us are driven essentially by enzymes. The metabolisms, have happen in our bodies only happen, because of the enzymatic reactions. And enzymes only work at very specific pH ranges, which can only be obtained, if at all you use a buffer. So very important. So the way you make buffers is you exploit what you already know, the Henderson-Hasselbalch equation that you guys actually know about. Now I'll just show very quickly how you derive the Henderson-Hasselbalch equation. Now if you had an acid, such as Ha, and just a symbol of an acid, meaning it's a monoprotic acid, just one proton. I know Ha can hydrolyze, or rather can dissociate, the Ka1 to give you the base, the A minus, plus, the proton, the proton, which is what I have right there. Now, if I put it, in the equilibrium expression, I'm gonna take, the Ka, is equals to the products, divided, by the concentration of the reactants, and that is what, I essentially have here. If I take the negative log, of both sides, of this equilibrium expression, I get something that looks like this. And of course, we all know, negative log, refers to or is symbolized, by a small p. And that's what I have here, the pKa. And that's what I have here. The negative log of the hydronium ion is actually the pH, plus, the log of, what's on the top, the conjugate base divided by the conjugate acid. So essentially, you can see that is the Henderson-Hasselbalch equation, which you get it, right from the equilibrium expression after taking the negative log, of both sides. Now remember, there are different variations of the Henderson-Hasselbalch equation. For example, similarly, if at all I had a base instead of an acid, that hydrolyzes, to give me BH plus, plus the OH minus, I can take the negative log of both sides to give me another form of the Henderson-Hasselbalch equation. In this case, the POH is equals to the pKb plus, the log of the acid divided by the base. All right, and that's what I have here. I've already derived it for you here. The different variations, of the Henderson-Hasselbalch equation. In this case, that's a weak acid. In this other case, that is a weak base. All right. Now, of course, when you're dealing with a diprotic acid, you can have up to 2 different buffers, right? Because you're dealing with H2A, which is a diprotic acid, meaning it can undergo 2 sets of hydrolysis or 2 sets of dissociation, to give me that, plus the hydronium ion. But also this one is an amphiprotic species that can further undergo dissociation, the Ka2, giving me the A2 minus, plus the H plus. And you can see, if I get, the equilibrium expressions here, and I take the negative log of both sides, I get 2 Henderson-Hasselbalch equations. So you can see all these are different variations of the Henderson-Hasselbalch equations, which are actually used, to make or to determine the pH, of buffers. Remember, as I said before, a buffer is a conjugate base and its acid pair. I'll give you an example, of where you can use the Henderson-Hasselbalch equation. Take an example of this type of base. You've got trees, which is a base. Its structure looks like this. You can see it, You can see it's an ammonia, it's an amine based compound, so it's actually a base. It can be protonated. So this one is a conjugate acid, and this is, a conjugate base, okay? So 12.43 of a conjugate base, and the molecular weight is 121. Again, the concentration of that. On the other hand, I can get, the 3 hydrochloride, which is this guy, and I weigh 4.67 divided by the molecular weight, it's that, and that's a concentration. And then I just need to substitute it, into my Henderson-Hasselbalch equation so that I can determine the pH, okay? And all I need to do is get the pKa substituted here, plus, and I'm sorry, I forgot, there's log here, there's a log there, log of B divided by BH plus, and then I can determine, what the pH is. And those of you in biology, I'm sure you've come across trees as a very, very common, biochemical buffer system, that is used in physiological or biological systems. So another way to make the buffer, so in this case, I went to the shelf and I got the base, I weighed it, I dissolved it in water, and then I went and I got the acid, the conjugate acid from the shelf. I weighed it, I dissolved it in water, I mixed it up, and that's the way I made the base, or rather the buffer. But another way to make the buffer is you just take one of the pairs. In this case, I just take the acid, the acid form, and then I try to make the base form just by reacting it, with a base. All right, so in this case, I took the acid form and then I reacted it, with the base, hydroxide. And we know acids react with bases, to give me, the other form, the base, and of course, plus water. It's a neutralization reaction. You can see it's a neutralization reaction. It's a neutralization reaction. So if at all I do not have in the shelf, both the base and the acid, I can just take, the acid form and do a reaction, by adding the base to give me, the other form. And then based on that, I can actually calculate, the pH, of my solution. And how do I do that? So initially, I had this number of moles of the acid that I got from the shelf. I weighed 10 grams divided by the molecular weight, which is that. I get the number of moles. And then I determine how many moles of hydroxide do I need to add, into this so that I can get a portion of this being transformed into a base, the acid being transformed into the weak base so that I can have the pair, the acid base pair. And so in that case, the X is what I'm adding. I don't know. I want to determine that. And so after the equilibrium is reached, this is consumed. So 0.06 minus X. This one is essentially consumed. So it's equals to 0. The base that I add, all of it reacts. And then I make the product that is formed, it's X, right? It's a one-to-one stoichiometry. And I can substitute it into my Henderson-Hasselbalch equation. The pKa is known, plus the log of the base that is formed, divided by the reactants, which is that. And you can see my X when I solve it is 0.016 moles. And that is the moles essentially of OH, that I added. And so finally, if I know the moles, we know moles is equals to concentration times volume. And I know the concentration, of the hydroxide that I added. So I can calculate, the volume, that I added or that I need to add, to make a buffer with a pH of 7.6, using only one acid in this case. I just take the number of moles, divide by the concentration of the hydroxide, and you can see that 2.0 mils is what I need to add, of the base is what I need to add, to 3's hydrochloride. So hopefully that's very clear, that we can make buffers using only one, only one of the pairs. In this case is an acid. I only need to react it, with the base so that I can form, the other base pair. So the other thing that I'm gonna like to highlight, is acid-base titration curves. In fact, you can see from my previous reaction here, essentially this is an acid-base reaction. You can see it's an acid that I'm reacting with a base. If at all I was doing a titration, essentially, the titration curve would look like this, where I'm measuring the pH, all right? And I'm adding the base, like in the previous reaction. And so as I add the base, of course, the pH keeps rising. And then it reaches a point, where I've consumed all the acid, that is present. All right. And that is what you call equivalence point, very similar to what we talked about last week. Equivalence point, the VE is an equivalence point, meaning I've consumed all the acid, that is present. And then I continue adding my base, and then I get it plateauing. And that is what I call, a titration curve. And the most important thing at this point, this is when I've consumed all my analyte, by adding the titrant, from the burette. Okay. So I'd like you to know some of the features, of the titration curve. Of course, the most important is that midpoint, or that inflection, is what you call the equivalence point, or the equivalence volume, or sort of the end point. Now, another important, mark in the titration curve is that point here. And this point is equals to half the equivalence volume. So if you take the equivalence volume is that one, VE. If you take a half of the equivalence volume, you get that point here in the titration curve. And the pH is equals to the pKa at half the equivalence volume. Very, very important, landmark in your titration curve. In essence, you use this, to determine the pKa. Remember, all these are constants, that you get in the tables. How do they normally obtain them? They normally obtain them by doing a titration, and then they determine, the half equivalence volume, that is the pKa, the pH is equals to the pKa at half the equivalence volume. So take note of those two benchmarks, that point and then that point. Very, very important in volumetric acid-base titrations. Okay. Now, we are always concerned, on how big, the inflection point is. When you're doing your titration curve, ideally, you want your inflection point, this region to be very, very sharp. The bigger it is, the steeper it is, the better in terms of you determining, the end point. Meaning, it's going to have a very sharp and clear end point, okay? And so the end point, or the equivalence volume, is determined, by two things. One, the concentration of the analyte. Okay, so you can see, for example, in this case, I've got different concentrations of the acids, and I'm titrating them with a base. And you can see the higher the concentration, the steeper, the inflection point is. You can see when the concentration reduces, I get a very shallow, very shallow inflection point, meaning the end point, becomes very fuzzy, and that's not good. You're getting, to the limits of detection when you have very low concentration. So ideally, of course, you want, a higher concentration so that the inflection point or the end point is very, very clear. All right, so the acid-base titration curves are determined, or one parameter that affects the equivalence point, is the concentration, of the analyte. And, the other factor that affects how steep, the equivalence point is a pKa, all right? So you can see in this case, if at all I've got a pKa of 2, you can see my inflection point, is very, very large. On the other hand, if at all I've got a pKa of 10, meaning I've got a very weak acid, you can see my inflection point, is very, very shallow, and I would have a very big difficulty, trying to do a titration for a very weak acid. Okay, so you can see a strong acid, I get a very good inflection point. For a very weak acid, I get a very shallow inflection point, meaning I'm gonna struggle to determine that end point. So in the next lecture, we're gonna talk about polyprotic acids and bases. So you can see for now, we've talked mainly about monoprotic acids. Monoprotic acids meaning it's got only one proton, that can be donated. And so in the next lecture, I'll very quickly talk about, the polyprotic acids where I've got more than one hydrolyzable proton.